Mallows CP, yeah, okay. So we're talking about selection of models and selecting the models based on different criteria and different methods to do that. So we talked about Mallows CP, and then I had to put off talking about the AIC criteria. And AIC is not even discussed in the book, I don't think. But it's really commonly used, and then it is used a lot in time series. So if you've already had time series, you would recognize that. So I'm going to go ahead and talk about it. But my experience with using AIC in multiple regression setting is that it and CP almost always agree. So it's rare to find a data set that those two differ in which model is the best. But AIC stands for Akiiki's information criteria. Does anybody remember how to spell that name? Neither do I. That's why I was hoping you did. The AIC criteria, the C is for criteria, and then it's just Akiiki's information criteria, right? And I can't remember how to spell it. Akiiki, something like that. So I'll put spelling. It's in the SAS help. If you click on SAS help, it'll spell it out for you. But it's a Japanese guy. So that's a Japanese name who first proposed this. And I won't even give you the formula for it. The formula is based on the log of the likelihood function. Now, if you've had 345, you've had to do maximum likelihood estimation and those kinds of things. If you haven't had that class yet, you'll get that probably next semester, right? You guys are taking that? So it's based on log likelihoods, and Mallows CP is based on least squares estimation, and so it's based on sum squared error, and this is based on likelihood function. So it's similar, but it'll give slightly different values. But like I said, in multiple regression, it's almost always the AICs will minimize at the same place that CP minimizes. And for both of them, that's what you're looking for. I want the model that has the smallest value for that criteria. Okay? So smallest is best. Now, it's very common that the AIC goes negative. So then it's the biggest negative is the smallest. So that can kind of fool people sometimes. Whereas the Mallows CP does not go negative. So negatives are possible. So let's throw away that marker. Let me turn on the projector, and I've got an example problem up here. And this is the soil evaporation data. Remember we talked about that several times already? I think I even used it on your test. But the data I've created, just so we don't get hung up in what the variables are, and it makes cleaner output. I've just defined variables. Y is evap, so that's the evaporation rate. And then x1 is day, x2 is whatever, right? So I've just called them all x1, clear up through x11. Right? Did we talk about, remember we talked about, well, it's not an average. Well, I went and looked it up. I don't remember if I ever remembered to tell you, but they aren't averages. The A, like the max AT, I thought, or not, that's air temperature. AVAT is not the average air temperature. It's like area under the curve kind of thing. So it's a measure of average, but it's kind of a weighted average across the day kind of thing. So we were looking at values thinking, well, that doesn't make sense, but that's why. It's area under the curve. So anyway, not important for this discussion. If we look at the correlation matrix, I showed this last time. Actually, I showed it for a different data set, I think. But if you kind of start with the correlation matrix, and this does not quite show all of them. Make that a little bit bigger. Yeah, I can't quite get it on there, but there's the bulk of it right there. So the correlation matrix is just the raw correlations between each pair of variables. With y with each of the x's, that's the top row here, and then each of the x's with the other x's, and so on. Right? So what are you using the raw correlation matrix for? What do you look at it for?
To see correlation between variables.
Okay. You're looking for really two things: collinearity, and then correlation with the y variable. Right? So you're getting a hint as to which variables seem to be most important. So if I look at x1, that's not very strong correlation with y. This one's pretty strong at 0.76, 0.68, negative 67. There's one that does not seem to be correlated, and so on. Right? But then you're also looking for ones that might be collinear. So you're looking for out in the middle of the table ones that are above what would be concerning. How big is concerning? Yeah, about 0.95 is where you start to get worried. If they're more highly correlated than that, then you may have collinearity issues. But even if they're like 0.84 or something like that, it still can affect the model. It won't affect the algorithm that's used to produce the model. So you won't get your standard errors blowing up or anything like that. But you can still have an issue with one variable causing another variable not to look important when in fact it is important, or vice versa. So here's one that's 0.81. That's x7 with x6. There's a 0.87. So we're going to have some we need to look at, right, when we do this model building exercise. Okay? So we've talked about mallow CP. Let's go ahead and run the AIC and the CP next to each other. So I'm going to clear that output. And I showed you this code last time, right? Does everybody still read that okay? It's highlighted. So I just have all of the variables in there, x1 through x11. Then I have a slash. I put it down the next line, doesn't matter. SAS doesn't care about line breaks or spaces or whatever. It's the semicolon that matters. So a slash, and then selection equal r squared. And I don't really want to use r squared, but it's going to sort it with the best r squared first and then down. So it's a way of sorting. Then I want it to print the MSE, the SSE, CP, and AIC. All right, so that's, you can ask for, you can click on the help button and look at the syntax to see what other options are, what other statistics you can have it produce. But, and there's several others, but not a lot of others. And then do you remember what the best equals 6 does?
Because there's so many, you choose the top 6 for each category.
You figure, well, if it didn't make the top 6, then it's not a candidate anyway, so you don't want to show them all, you just have reams and reams of paper. Okay? Then some of these other, I have an asterisk, a semicolon, and an asterisk right there. So this is just a comment. But I've commented out some other options that we'll talk about. Probably by the end of today, we'll talk about these last two. SL entry and SL stay. SL for selection. But let's run this for now. And with 11 variables, you get lots of stuff. Right? So, number in the model. So this is the best 6 one-variable models. There would be 11, but it's not showing me the other ones. Right? So remember, we had some that weren't very highly correlated with Y at all. They're not even going to make this list. But it says the best the best single variable is x2. And it tells me all of the statistics. So it has a R square of 0.59, a CP of 43 point something. Now, remember our discussion about CP? When does CP start to be in the range of, okay, things are getting good? When it gets down to what?
It's less than
K plus 1, right? And K is the number of variables. So this would need to be 2 before I get very excited about it. So the fact that the very best one is 43 tells me you need another variable in this model, right? Your model's not doing that great. Okay, and then AIC is 208, then mean squared error and sum of squared error. And notice the mean squared error is quite a bit better than the one right below it, because you want mean squared error to be small. Right? Then if we go to the next block that has 2 variables in it, notice that the best 2 variable model does not have x2 in it. That's kind of unusual, but this is real data actually, and so obviously that does happen. Right? X4 and X6 do better than X2 does by itself, and in fact X2 doesn't show up till the next model down, and the second best 2 variable model has X2 in it, but also X1, so completely different. Right? So X1 and X2 are explaining not quite as good as X4 and X6, but when you have 2 variables, it's the combination of those 2 that you're looking at. Right? Okay, so by Mallow's CP, where's my best model?
3.
This is where it's minimized. Right? So CP is smallest at 3 variable model, and the 3 variables are X1, X4, and X6.
So that's just based on Mallow's model. If we wanted to go based on root mean squared or based on MSE, you would use one of the 41s, whatever, which one of those was the lowest.
Yeah, and look at MSE. It's 89, 59, 42, 41.26, 41.38. It starts going back up. Right? And remember, MSE takes into account, through its degrees of freedom, the number of variables that are in the model. So it can go back up, whereas R square cannot go back up, or cannot go back down. It always goes up until you get to the 11 variable model. Right? But it ends up not going up by much. In fact, look at the 3 variable model. R square 0.8169. If I go all the way to the 11 variable model, .8383. Now I already forgot what the other one was. 0.81 something, right? So it only went up about 2 percentage points from when I added in 8 more variables. So you could do a partial F test to see if the inclusion of those intervening 8 collectively give you a statistically significant increase in your R squared. And what you'll find is, no, it's not statistically significant, because I didn't. Okay? Now look at the AIC criteria. I guess I didn't scroll all the way down to confirm that CP was best at a 3 variable model, but it seems to be going up, and I don't know that I have a proof of this, but CP will never bounce like that. Once it bottoms out and starts back up, it never comes back down, right? So you don't have a problem with a local minimum, global minimum. It's just, so once it starts back up, you don't really have to look at the rest getting down. Okay, then AIC. So where does AIC bottom out?
Yeah, so 3, same one.
Same one, 175.797. This is 175.826, just barely different. And this one is actually a little bit smaller than this one, but still bigger than that one, right? So that one is the minimum AIC, so it agreed with mallow CP. And like I said, they almost always do agree. Okay, so AIC we won't, I won't make you compute it, but I may give you a list of them, say by AIC criteria, which is the best, but that's easy, it's just whichever one's smallest. But just remember, if they go negative, then you have to get the smallest by being the furthest away from zero. It's always,
The CP doesn't have negatives?
CP will not ever go negative. Okay, now we'll talk about some other selection methods. The methods that we've talked about so far are basically computing a statistic from the model and then finding the model that has the best value for that statistic. So R squared, the best value is bigger, but it doesn't work very well. But adjusted R squared would mimic mean squared error in where it would minimize out, because it's based on mean squared errors. R squared is based on the sum of squared errors. And then CP criteria, AIC criteria, again, you're just looking for the one that has the minimum value for those. Now there's other procedures. There's 3 procedures that are all real closely related. First one is called forward selection. And then backward selection. And then the third one is stepwise selection. And the book talks about backward and stepwise, but does not talk about forward selection. And that's because, as this will illustrate here in a second, sometimes forward selection doesn't perform very well. But it is an option, and it gets talked about, and people use it, so you need to be aware of it. And I like to teach forward selection just from the perspective that it's a good place to start learning what it's doing and then say, okay, but here's how we can improve it. So forward selection. What you do first is you fit all one variable models then choose the x, I'll say x variable with smallest p-value which is the same as saying the biggest absolute value of t statistic. If it's a one variable model, then the f statistic could also be used, but we'll just stick with the t. All right, I said I put absolute values around it because it could be in the negative side, it could be in the positive side with the t statistic. Then let's see. Then choose the x to be entered and I'll just put it in quotes, to be entered. So we're building a model here, and so we're going to enter variables, and then we're going to remove variables from the model. Right? So forward selection, you start with no model, basically an intercept-only model, and you're going to add variables to it. So you're going to go forward from 0 up. Right? So let's do this step. So what I'm going to show here, I'm going to limit, I don't want to have to make it go through all 11 variables, so I'm going to limit to 4 variables. But here is a proc reg that has 4 model statements. So proc reg will allow you to have multiple model statements, and it just fits them all. So model y as a function of x1, y as a function of x2, x3, and x4 separately. So I'm limiting to just to the first 4 of those x variables. So I'm going backwards now because it comes in at the bottom. But the p-value for x4 is less than 0.001. And I page up and there's x3, same p-value. x2, same p-value. x1, there's one that's bigger, 0.0336. So since SAS is writing them out as less than 0.0001, I have to go to the t-statistic to decide which one I'm going to put in the model. So, memorize the numbers as they go by. So we know x1 isn't the one because it had a p-value of 0.03. But here's x2, and it has a t-statistic of 7.99. Got that? Next one was 6.28, so not as good. And then the last one, negative 6.02, so again, not as good. So for this one, we will enter x2 into the model. Right? So I'm building my model. So right now my model is beta 0 plus beta 2 x2, and I'm just matching subscripts on the betas, even though I don't have a beta 1. Right? So that's my model. I'm building my model as I go. Right? So what do you suppose we do next?
Take that one out or no, leave that in.
Leave it in. Good. You leave it in, and then you take all of the other variables one at a time and add them to x2 and see which model is best. Right? So then add each remaining x one at a time. That's not how you spell at a time. At a time. To the current model. Choose the smallest p-value again, same kind of thing. Okay, so that's this code. We decided x2 went in the model, so all 3 of these models have x2. But then I add x1, then x3, then x4 to the model that has x2. Okay. What I'm going to do, when I walk over there, it won't show the screen on the video. So I'm going to leave that there. Hopefully you can see at least most of the screen. So this is again at the bottom, and I'm going to go up. But here's x2, x4 being added to it. It has a p-value of 0.0927. Okay, I'm dyslexic. 0.0297. Right? So it is statistically significant. But when I page up, x3 is not statistically significant. So right now, x4 is my best, but I got one more to check. And there's x1, and it's 0.0003, so that's better. Right? So at this step, we would enter x1. Right? So we come over here, and we add x1 to the model.
When you might have said this already and I didn't catch it, but when do you stop?
I haven't said it yet.
Okay.
Right? But that's a great question. When do you stop? So, what would the next step be? I'm doing only 4 variables here, so we're going to do a dot, 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 continue till you stop. What would the next step be?
Run the model with those two.
Run the model with those 2, add the remaining ones one at a time. So, step 3, using current model. Add remaining one at a time, yada yada. Pick the best one, right? So now you can just kind of say, you get the pattern. So if I run this, I've got x2 and x1 in the model. And then I only have 2 more to choose from, x3 and x4, so I'm going to run each of those and see which one's best. And there's x4. Is it significant? No, x4 is not significant. x3, not significant. So when do you stop?
When the next one is not.
When none of them are significant. None of the remaining ones are significant at a pre-specified level of significance. Then you stop. Right? So remember the SL entry thing that I said this is an option with? That's the pre-specified significance level to enter into the model. If I enter at 0.05, then I'd be done, because none of them are significant at that. Let me page back down to x4. That one is 0.1073. If I set my alpha for entry at 0.10, this one would barely miss, but it still would miss. But if I set my entry at 0.15, this one would then get in. And it's common that it's not set at 0.05, which is what we're used to for significance, that it's set at some value a little bit higher than that. But it can affect the model. A lot of times it doesn't have a great effect on it. But the reason we usually let, the most common would be 0.1. And the reason we use 0.1 is because if something is 0.06, they say, you know, that's still explaining quite a bit of variability. It's not quite at the 0.05 level, but I probably want it in my model.
So can you use this type of selection if they only want a certain number of variables?
No. I mean, you could modify the algorithm to say, do this until you get that number and then stop. But
Okay.
all right, so you stop when no remaining variables are significant at the SL significance level for entry. SL is usually 0.05 or 0.10. And 0.10 is probably the most common, and it is the default that SAS will use. If you don't tell it, it'll use 0.1. Okay, so if I go back to the code,
Sorry, 0.05 is one of these SAS uses?
no, SAS will use 0.10. Now, you may be thinking, man, I hate to have to do this by hand and run all these regression models. So SAS has it built in with a forward selection procedure. So if I run, let me run, I'm going to copy this code up here and run it using the automatic, which I thought I already had there, but apparently not. But I'll copy this code up into my forward selection part of this program. And I'll put a slash selection equal forward. And then I showed you that code down here somewhere, SL entry at point 1, SL stay, that's to stay in the model as soon as we go to the backward elimination. Right? But I'm going to just let it default on that for now, and we'll just run that.
So because those are point one, you wouldn't have to specify them, because SAS would just go through that anyways.
Okay, so here is the top of the output. And it says, oh, I got my title wrong. I copied that code from below, but I forgot to change the title. So the title doesn't affect it. But, it tells me number of observations read and used is 46. Forward selection, step 1. So then in step 1, it says variable x2 is entered. It gives me this r square and this CP value. And I forgot, I'm going to delete this output and rerun it because I like to add another option here, details. Because I want to see the details of each of those steps. I want to know why did it put x2 in there, or how close were the others to x2. So it'll show me those p-values that we were looking at a minute. So I'm going to rerun it, and I'm going to change this to, say, forward. Okay, so now it tells me forward selection step 1, and then here's the details. So x1, 2, 3, and 4. Here are the F statistics. We were looking at T statistics before, but with one variable, it's the same thing. But you're looking at the one that has the biggest F value, which was x2. So it says variable x2 is entered. Well, that's what we did over here, right? That's the first one we entered into the model. And then we go down. Here's the model itself with x2 in it. But if I page down, it'll say, okay, next step. Oh, and down at the very bottom. Oh, no, that's not. I thought it was going to tell me what those entry criteria were, but it says bound condition. So here's forward selection step 2. Now it gives me the other 3 remaining variables, x1, x3, x4. Gives me their p-values. I picked the one with the smallest p-value. That's x1. So x1 is entered. And it goes into the model. Then it tells me the model. Shows me what the current model is. Forward selection step 3. Look at that. X4 p-value 0.1073. It says variable x4 was entered. So it put it in the model. So I must be wrong about what the default is. The default must be 0.15. So if I put SL entry equal 0.1, then this one wouldn't make it in, but just barely. Right? And we'd settle on that same model. Right? But then, so now we have a model with x1, x2, and x4. And the next one, the next step, says no other variable met. Oh, the 0.5 significance level. Yikes. So yeah, you probably don't want to take the default.
You can kind of just go with that though, and then you can just look at it yourself.
You can look at it and say, okay, here's the one I want. Okay, and then it gives you a summary of each of the steps. So step 1 we added x2, step 2 we added x1, and step 3 we added x4. Right? Okay, so backward selection. Any guesses how that's going to work?
So have all the models in there and then pick one out. Whatever.
You start with all 11, so I'm not even going to bother to waste the ink on the board. you start with all of the candidate variables, all the potential variables is the term the book uses. And you fit the model with all of them. All right? Then you start looking at the p-values for all those variables. And whichever one is the biggest p-value, or the smallest t-statistic, then you'll yank it out of the model. So we don't need that one. And then you refit the model with the rest of them. So, again, limiting to the first 4 variables, you would start with the model that has all 4 variables. You're looking at the p-values, and you pick the one with the biggest p-value, 0.6062. That is x3. So x3 would get removed from the model, and so on. I won't go through the whole thing this time by hand. Let's just bail out and use the backward selection procedure. So I'm going to take this code and tell it to fit with backward selection instead of forward. So selection equal backward. Only this time I'm not going to accept their default for now. Instead of significance level to enter, it's significance level to stay, right? Because they're already all in there. Now you're taking them out. To stay in the model, it has to have this p-value, right? So I'm going to put SL stay equal 0.1. And I'll go to the top of the output and we'll work our way down. So backward elimination, step 0, and saying, here's the model with everything in it. Right? And then backward elimination, step 1, page down. There are the p-values to look at. And it will choose that 0.60 and say, okay, x3 goes away. So variable x3 removed. The model that you're now sitting at is 1, 2, and 4 in it. And you're going to look at the p-values. This one is bigger than my 0.1 criteria to stay in the model, so it should kick that one out also. I have to scroll down to see. Yeah, it's kind of, there it is. Okay, so it says, backward step 2, variable x4 is removed. Okay. Then it should be done because everything that's left in there should be significant. So it gives me the message, all variables left in the model are significant at the 0.10 level.
So backwards goes to 0.1 and forward
We
goes.
specified that in the
Oh.
Yeah, I specified it this time.
Can you show me the code for that again?
It's SL stay, right?
Yeah. So here it is right here. You say SL stay to set that one. Up here, if I added SL entry equal 0.1, then that would change the default. Okay? Easy enough. There's one more, and it's called stepwise selection. Guess what stepwise does? Combines the two. It uses forward selection to begin with, but then at every step after it adds a new variable, it checks the other variables that were already entered to see if maybe one of them should get kicked out. Because sometimes, we've talked about this, sometimes when you add a variable into a model that's correlated with one that's already in there, the one that was already in there is no longer needed. So the stepwise procedure is really the best of the procedures. So let me run, I'm just going to run this same code that I did a second ago. I'm going to change the word backward to say stepwise. And I'm going to put SL entry.
So now you have to have both.
If you want to, yeah. Now, if you want to control both, you have to type both in. If I didn't put the SL entry, it'd still use that 0.5. Okay, so did I clear my output? No. So now it starts in the forward direction just like before. At step 1, X2 is entered just like before. And so I'll hurry down through these. At step 2, it says X1 is entered. That was exactly the way it did when we were going through forward. But now also it wants to check, is X1 or X2, which was already in the model, is X2 significant at the 0.1 level? And it is. You see with the two variables down at the bottom, both of them have highly significant p-values. So both are going to stay in the model. Nothing's getting kicked out. Then at the third step, it says all variables left in the model are significant at 0.1. No other variable met the 0.1 significance level for entry. Right? So it says, oh, we're done. I don't have any I can remove. I don't have any to add. So all three of those procedures, when we set it at 0.1, settled on this same model. Now let's run it with all 11. And we'll just do the stepwise one. If you have software that will run the stepwise procedure, it's almost always the one that is preferred. That's the one that people would choose. So, well, since I can do it all, we'll just go to the bottom and see what model it settles on. I'm going to do forward selection with all 11, and then backward, and then stepwise. So we compare, because I don't think they're the same now. So forward selection, down at the very bottom, it says no other variable met. Here are the ones that were candidates. None of those are significant at the 0.1 level. So here is the summary of forward selection. X2 went in first, then X1, X6, and X4. Okay? So we settled on a 4-variable model. I'm going to keep track of this because I won't remember.
I just wrote it down. X2, X1, X6, X4.
Okay, so then this was forward, right? So forward was X2, 1, 4, and 6.
Does it matter that you switch the order of X6 and X4?
It doesn't really matter, but I want to keep them in the same order because we kind of see the steps that occur. Okay, so then let's do backward selection. And I need the page up to see the final model. The final model is this one with X1, X4, and X6. Right. Then it's checking and it says all variables left in the model are significant, so it's saying it's done. Right. Well, it's done if there's no more that are significant to be entered, but since I paged up from the bottom. So here's the summary. Right. This is backward selection. So the first variable removed was X9, then X7 went out, X5 went out, 10, so on, and then X2 went out, and X11 went out. So backward settled on a different model than forward. We end up with
X1, X4, X6.
okay. Now let's see about stepwise. So the final model, we're getting the bottom part of the output up there. There's the final model, x1, x4, and x6. So stepwise and backward agreed. And look what happens here through the summary. First step, it entered x2. Last step, it took x2 back out. So this is a good example of where stepwise combines the two. Right? It still allows something that got put in early to then to decide that, oh, you know what, it's not important anymore. Let me hit one more page up, just a second. I want to see the model that had x2 in it, where they say at this step x2, there it is, x2 is removed. So I need one more page up, right there. So after x1 went in first, but then after 1, 4, and 6 got put in, now all of a sudden 2 becomes not significant. So then it gets removed at a later step. Okay, you had a question?
Yeah, I'm having difficulty seeing how stepwise will result in anything different from backward.
Suppose that x2 had stayed significant here, right, and not get removed, then, well,
Wouldn't it have also stayed significant in the backward model?
quite possibly, yes. But when you get differences between them, it's because there's correlation between the variables. And so if you start backward, it's possible. It's hard to find an example data set with real data where it happens. But it's possible that all three of these settle on a different model, right? And then stepwise is generally preferred because it combines sort of the best of both of these, right? But it is possible that stepwise will settle on something different than backward, because it's actually starting at the beginning with no variables and working its way up. So backward, suppose x11 was a variable that was only significant when three other variables were in the model, certain other three variables. So there's a correlation between those four variables, right? So in forward selection, it might not ever make it into the model, right? But with backward selection, it's going to stay in the model as long as those other variables are in the model. But since stepwise starts in a forward direction, it may never have the opportunity to drop that one in because the right combination of the other three never gets there. So it can happen, but like I say, it's really, it took me a long time to find a data set that just had a difference between any of them, right? Most of the time they all agree. It's just, but when you have a sufficient amount of correlation between the x variables, then it's when it starts to really affect things. So this data set happened to have x variables that were closely related to each other because some of them have another one kind of built into it. Right? Current soil temperature is part of average soil temperature. Okay, let's see. Any questions about those model selection procedures? That's all of them that we're going to talk about. There are other criteria out there, but none that really do anything different. They just use a different way to compute a number or whatever. So, all right, well, if there's no questions, we'll go to the next section, which is residual analysis. Once we've settled on the correct model, I shouldn't say correct model, once we've chosen a model that we feel is best, now we got to run some diagnostics on that model. Right? So what do we mean by diagnostics? What do you say? Okay, residuals is a big part of it. Are there influential points? Is there any, any of the assumptions for multiple regression, are any of them violated? Right? So once I settle on this model that has 4 variables in it, then I better check, do I have any collinearity between those variables? Do I have other strange things that are going on? So let's start with the very basics. What are the assumptions in multiple regression that involve residuals?
They have mean 0.
Okay, residuals have a mean 0, right? Now, when we use least squares estimation, our sample residuals will, by definition, have a mean 0, right? So we don't have much of a way to check that, but that is one of the assumptions. What's another one?
Constant variance.
Constant variance. The residuals have to have constant variance. And that we can see from our residuals, our sample residuals, because they might have low variability in the beginning, but as X gets bigger, they flare out or something, right? And then
Are they independent of each other?
they have to be independent of each other, and then kind of goes along with the same thing. I wrote down functional form. Like if you're fitting linear terms for all of them, then all the residuals should show random scatter and no curved pattern or anything like that, right? So that's part of independence. If there's a curved pattern, say, hey, these aren't independent of each other. In time series, we learned that we have something called autocorrelation between residuals. If you get a residual plot and you notice that if one of the residuals is positive and the next ones tend to also be positive, but once that goes negative, then they tend to stay negative for a while, that's autocorrelation between them. So you see a pattern in the residuals. So basically, any kind of pattern you see in residuals is probably not a good thing. You want to see random scatter. What about normality? Can you see whether or not your residuals are normally distributed by looking at a residual plot? Not typically. It's hard. There are some, and I used an example either on, I think it might have been on your last test or on the last review sheet for the last test. We had one, see if this rings any bells with you. We had one where we had the 0 line was about right there. Right? And we had really heavy points around that 0 line, and then we had some smattering of points that would go up, but none that went down. What would that tell you about your residuals? They're not, they're skewed, right? Not normally distributed, they're skewed toward the positive side. You tend to get really big positive residuals, but no really big negative residuals. Right? So then that's a case where you can kind of tell something about normality. But generally it's difficult. So we have another kind of plot we look at. You remember what those were?
It's a normal plot.
The normal plot. And what is a normal plot? Yeah, and I wrote down here, it has 3 names. A normal plot, a PP plot, or a QQ plot. And they really all do the same thing, slight differences between them. But a normal plot is kind of a generic term just to say you're going to plot the observed residuals against what you would have expected if they had been normally distributed, and you see how well those things agree. So let's see if we can get SAS to produce some of these different plots. And what I have here is a program where I simulate some data and I impose some definite problems with these things, but then I show how to get some of those plots. So I've already run the data, I believe. So let's do the y variable is is called post, and it was a pre-post kind of thing. So post means the after treatment measurement or whatever. So here's a graph of it. And again, I made this data. I simulated this data. So what are we looking at there? What's the problem?
Increased variability.
Increased variability. You see that as x gets bigger, the variability is increasing. It looks fairly linear, which is good, but it's definitely got a problem with normality. Well, if I fit a model to this data, so post on x, and I ask for a residual plot, and this is old code, so this is old school SAS, but I can turn my ODS graphics back on and get their default ones, which are prettier than the ones I could make. So I'll say ODS graphics on, and then I can comment out that plot statement. But you can plot lots of stuff, right, using these plot statements within a proc reg. But if you turn the ODS graphics on and let the new version of SAS 9.4 run, it'll give them all to you. And a lot of times it's more than you want, but you can go through and pick off, oh, I wanted to see that one, so then you can look at it. So let's run that. It takes a lot longer to run when you do all these graphics, but one of these days it'll pop up. Or not. There we go. Uh-oh. I wonder if I had other options I had to turn off. Graph. Well, sorry about that. I will have to try to undo the line of code I did up here. So I did ODS graphics off, ODS HTML close, and then ODS listing.
So if there was, like for that example, there was just increased variability, would you just say a multi a multi-linear regression is not appropriate for this model?
So where do you log it? I guess you would.
Yeah, I'm going to do the log transformation here in a second, but yeah, so you try different things. Maybe linear is not appropriate, so let me throw a quadratic term
Just
in.
try to transform the data until you get what you want.
Exactly. So ODS listing, I don't know how to turn that. I think it's off. I'm experimenting a little bit here. If I don't, I'll go back to the old school way of producing the graphs, but it's not off. That still didn't work.
Can you just open a new session?
That's what I was just going to say. Well, you know what I'm going to do? I'm going to close SAS. And then I'm going to open it back up. And that,
That's as bad because it thinks you thought it knew better.
yeah. Residual example, that's the one, yeah, that's the one I was running.
But yeah, if you just,
So I have to reload the data, but that's easy. And then I'll ignore all that code, just let it then have its default. I don't understand why it was taking so long to run and then still not giving me the graphs. It must be producing them, but then one of my other options said, okay, but don't show them. Now we got stuff. Right? So,
Looks cool, but
yeah, it looks really cool, but it looks really bad too. Right? Because you see that definite funnel shape. This is just a fit plot, so it's the same plot you saw before, only it has the line in it, and then prediction intervals, and they're hard to see here, but there's a real blur around that line, so it has confidence intervals around the line. let's scroll up and look at what kind of residual plots it produced. So there's your straight residual plot. Looks an awful lot like the other one, only it's not, it's horizontal now instead of tilted up. But clearly there's a homoscedasticity issue here. Alright, so here's a whole bunch of plots. This is residual versus predicted values. The one we just looked at was versus the x values. So this is y hat versus y minus y hat. Right? Everything's kind of looking the same. These are different versions of residuals. R student leverage. Have you heard that word before? What is leverage? That's the distance measure, also called the hat value. Right? So these are the hat values plotted against the studentized residuals. But here's the ones, the normal plots that we were talking about. Right? It says quantile and then residual. Right? So that means it's, oh, this is quantile from a normal distribution. And notice that this is standard normal, so -2, 0, 2. When you get out to 2 standard errors away from the mean, you're starting to get out into the tails. Right? What would you expect to see if things were normally distributed? You'd see it follows that line fairly closely. This line is basically the y equal x line, saying here's the observed residual on this axis, here's the expected residual if it's normal, so if they agree they should follow a line with slope of 1. But it does follow a line for a long time, and all of a sudden it shoots up. And that's saying the observed residuals are way bigger than you would expect them to be if they were normally distributed. So you've got a long tail off of that right side. This is the y values versus the predicted values. That's not telling me a whole lot. We won't get to Cook's D today, but it's in this chapter. We'll do that one. The one I was hoping for is probably, yeah, right there. A histogram of the residuals. So this is a histogram of the residuals with a normal distribution superimposed over it. And you can see that this tail is a lot longer than this tail. So again, you're seeing some skew in this data. I have no idea what that is. Okay? So now, strategies for fixing problems that you see in the residual plot. If the functional form is what's off, then you'll see some kind of functional form in the residuals. Like if you see curvature in the residual plot, oh, I missed a quadratic term that I should have in there or something, right? This one, the problem was the flare in the variability. And the log transform is often the first thing we try to fix that. So I'll try that. So this one is log of the post value. So it's been log transformed, and it's natural log. But log, it doesn't matter what your base of your log is, it has the same effect. So it's just personal preference, but most of the time I tend to use natural log. Now, that variable already existed. I can't just type log in front of the variable I want and expect Proc-Reg to know what it is.
You
Right.
can do that in GLN.
No. No, you have to have the right name of your variable. So it had already been logged up in the data step, which I didn't really show you that code. But that variable already existed. So I just don't want you to think the syntax is, oh, you just stick the word log in front of it, and you got to do it in a data step. Okay. So what do you see here? Now you see curvature, but it fixed the variability issue. Right? It didn't fix it perfectly, because if I think of fitting a curve through here, then I've got less variability around that curve down here than I do out there, but it stabilizes pretty quick. So the log transformation is sometimes referred to as a variance stabilizing transformation. So this is the residual plot not using the ODS graphics, but here's the same set of plots we were just looking at when you do use ODS graphics. So here's fitting a linear model to the log data, and you can tell from that also that, oh, there's some curvature that I missed, right? So that's pretty obvious. You do get nice tight bounds around the line, but and there's their version of the same residual plot. Now, what do you notice about these?
You now have issues at the beginning instead of the end.
On the QQ plot, quantile plot, it follows the line most of the way. The upper side, the right-hand side, now looks pretty good. But now it's a problem off of this side. And that will happen with log transformation sometimes. It overcorrects, right? So it brought in all of those outliers off of the right side, but it pushed some off on the left side and made outliers out of them. What happens if you take a log of a number less than 1? It's negative and it can blow up. In fact, where did I put my marker? If you graph the natural log function, it looks like that. And what's this number? That's 1. Right? So if you get numbers less than 1, you're going to get negatives back. So if there's any numbers in the data that are less than 1, they'll go negative. If they approach 0, they'll start to blow up in the wrong direction. Right? You're starting to shoot outliers off of this side when you pulled in outliers from there. Right? So my data, I just randomly generated data, so it's quite likely I had some values in there that were less than 1 that caused this to happen. But most of the time when you're logging data, you're logging things like cell counts or whatever. So they can, like the typical value is 10,000, and every once in a while you get a 10 million in there. So you log that data. You don't have ones down near 0 to worry about.
So just looking at this, would you try something different, or would you add something to the log?
No, I would probably stick with the log and say, yeah, there's not very many of those outliers, and I'll fit some curvature to this, and maybe I've solved both problems. So how do we fit curvature? All right, so up here in my data step, I have the log of the post. I have the post, and I have my x variable. SQ is x squared. Right, so I've created a variable already called XSQ. So if I fit that variable, let me clear this. Now it looks pretty good. There's still some outliers down here. But really, if I cover up these 4 points, that looks really good. Right? So I have a few outliers that I imposed just the way I generated the data, but that model looks pretty good. I don't see a functional form that I've missed. I don't see increase in variability.
It looks kind of like there's a fourth power.
Yeah, I saw you do this.
Yeah.
Right? But don't get fooled too much into that kind of thing. It's possible that's in there, but I doubt it. One of the things I always caution people on is don't let a few points tell you that you're seeing a pattern. Right? Like, for example, we'll see residual plots like this, and then there'll be a point out, and a point out, and a point out. And, oh, look! Right? But there's only 3 values. If I take those 3 out, then it's not that way at all. So now I need to address those outliers. I don't really need to log transform this data or anything like that. Right? So don't let a few points, like this little cluster down here, make you think that, oh, it's coming down. You know what I'm saying? This is a pretty big data set. If I page up, there's my residuals by regressors. So I have two regressors now, x and x squared. This one you've already seen, but the x squared one, they're clustered up near 0 because the x's are, x squareds don't blow up so fast. But look at the normal QQ plot. That looks acceptable. It's still not perfect, but I'd probably say, that's okay. I'd probably look into that outlier, maybe kick it out, and we'd be good. And off we go.
I can't remember, did we make this an x squared and then took the log of it?
I only logged the y variable. I
Okay.
did not log the x variable.
Right.
But there are times when you do log the x variable instead of the y variable. And there's times when you actually log both, right? I've got an example that I was going to show, but I'm out of time. So I'll do it next time. But an example out of an old book on term life insurance. And it's like the face value of policies that people take out. And they logged the face value because it was highly skewed data. But then they also logged income, which was one of the x variables. So you have an x variable that got logged and a y variable that got logged. So we'll look at that next time, and we'll talk more about this whole transformation thing and how it affects the model. All right, we'll see you Wednesday.